Hello, here with the Z proportion overview. This is our study guide from that unit. Just add some notes in here. Uh, First of all, let's talk about the one proportion. So on an AP exam, a couple things to just be aware of to determine between a proportion inference procedure and a mean inference procedure, and even a chi-square to an extent, is you're looking for things like percent, proportion, even a fraction, where you can tell that your sample data, okay, our sample data, which is p hat, versus an x bar in this case, where the p hat is a part-whole relationship. So you don't just want to look and make sure it's a decimal, because 0.2 could mean 20% or it could mean 0.2 pounds. But is 0.2 really a true 1/5 scenario or 20 over 100 or whatever it happens to be? So you're looking for scenarios where the sample data is a part-whole relationship. That's going to be a big giveaway. And then it will have a question like, is there evidence that the proportion of students who speed in the parking lot is greater than this percent, or estimate with a confidence interval the proportion of students who speed in the parking lot. So let's go through, with that context here, go through just a quick examples of one and two proportion just to see it in action. So first is a one proportion Z test here. A test on an AP exam is going to be a 4-point problem typically. If they have you do all parts, these would each be graded individually. And so it begins with the hypotheses. And so again, let's just say it's students speeding in a parking lot. So we might have a scenario where the null hypothesis is that 63% of students speed in a parking lot. And somebody else comes along and says, I think it's greater than that, or I think it's less than that, or I think it's something other than that. It could be more, could be less, but it's something that's not 0.63. So the alternative could be any one of those three. And again, that's the question. When you read the question, it will tell us which direction it's supposed to go. It may say that a teacher claims that it's greater than 63%, or a student claims that it's less than 63%, or a community member claims that it's not 63%, and it doesn't give us a direction, just says it's not 63. So the wording of the question will dial in that HA for us. Now, when you write these, as with anything in this course, if you have a P like this, you have to explain what it is. Okay, so you will write out in a sentence, in this case, P stands for the proportion of Minnetonka High School students who speed in the parking lot. Okay, and so the P again is not a sample. There shouldn't be a hat on these. It shouldn't be the proportion of our sample who speed in the parking lot. P represents the population, and if the population in this case is Minnetonka High School students or Minnetonka High School students who drive to school, then that is P. Okay, so you have to explain that. You can never leave a symbol or a single letter naked and not have an explanation behind it. So that's step one. That would be 1 point. Step two is the type and conditions. And so the type here, this is a one proportion Z test, and you would just note that. You could note it by name or by formula. It can be easier typically to just note it by name, so you don't goof up any notation with the formula. And in terms of conditions, there's two main conditions. There's a third one that might get referenced periodically. Okay, so the first of these conditions would be a simple random sample. Okay, so simple random sample here would be, again, would be something that would be stated in the question. We aren't going to be collecting this data. And so it'd have to state that it's a simple random sample of 50 Minnetonka High School students or something of that nature. Again, don't just say stated here. Just quote the question so you tell the reader how you know that. If you just say stated in question, that's a generic statement that doesn't give enough information. Second condition here is going to be related to sample size. And what this is really showing is that we have enough successes, okay, and enough fails that we can ensure that the sampling distribution would be normal. In other words, that it's a threshold that's really based on the combination. The closer it is to a 50% for P naught, again, P naught is the value in the hypothesis up here. The closer that is to 50, the smaller the sample size needs to be. If this were 50-50 for the hypothesis, then n would only need to be 20, okay, to ensure that we'd have 10 students who sped and 10 students who didn't speed based on our null hypothesis. If it's something further from 50, then that n gets bigger. So in this case, let's just say that it was that our sample size was 100. So we would just put 100 times 0.63 is 63. 100 times 1 minus 0.63 or 0.37 is 37. And you would note then for each of those greater than or equal to 10, and you would say something along the lines of it's a large enough sample. And that's the terminology that you'll see a lot with this, large enough sample. Okay, so that would tell us that our distribution, that we can trust it to be normal, which allows us to bring in the z here. Third condition that you'll see periodically is 10n is less than capital N, and this has to do with independence between the students selected to be in our sample, that they don't have a relationship that causes us to question the validity of our sample. And so this is just that less than 10% of the population is selected. So if we have 100 students who get selected, 100 times 10 is 1,000. Are there less than or are there greater than 1,000 students in our high school? Yes, there are. So we can trust that if we select 100, they will truly be 100 unique individuals. Obviously, if it's about driving students, that capital N is going to be a little less. Again, this is population here. So driving students might be, I don't know, closer to 1,200 maybe. And so in that case, that would be, we'd just barely be safe in that situation. Again, this condition, you may see it referenced. Typically, it's not required on the AP exam to list that. In terms of the calculations now, okay, so now that we have the first two steps have just discussed what we're going to test, that our data is valid, and now we're going to get to the actual calculation. And the calculation here, in this case, p hat, let's just say p hat was that 70 out of 100 students sped. So p hat would be 0.7. The p naught is the null hypothesis, so that's 0.63. And then the denominator, as you can see, would be the square root of 0.63 times 1 minus 0.63 over the sample size of 100. At that point, you're welcome to calculate it out that way, or on your calculator, you can go to stat tests, and this would be a 1 proportion z-test, which on mine is number 5. Make sure you don't go to 1 or just z-test. This is a 1 proportion z-test. There's a mean z-test as well that can be utilized periodically, but 1 proportion z-test. And when you get to that 1 proportion z-test, it's going to ask you to type in first the null hypothesis, or the p naught, which in our case is 0.63. And then it will ask for x and n, and that's just the numerator and the denominator. So that would be 70 and 100 here. Then it will ask for the alternative hypothesis. Let's say that we just chose not equal to for the alternative, and then we calculate. And in that situation then, that will give us the test statistic and the p-value. And what's perhaps most important with the p-value here is because I put in not equal to, it's giving us the two-sided p-value, which is 0.147. Half of that would be the one-sided p-value. Again, what we are now seeing is on this normal curve, our hypothesis was at 0.63, or 0 standard deviations from the hypothesized mean. We got a z statistic of 1.4. Again, this was at 0.7. This is at a z of 0, and this is a z of 1.45. So the area outside of that is about 0.0735. But then again, because it's two-sided, we technically look at this as also the area outside of here, which is also 0.0735, and that would be 7% below, which would be 56% or negative 1.45. Again, that's just because it's not equal to, okay? If it was a greater than alternative, we'd just worry about the blue, okay? If it was a less than alternative, we'd be on the left side, and we'd probably have a p hat that was most likely less than 63% in that situation. But this is the one-sided, two-sided nature there. And again, make sure to follow up on the meaning of that p-value, okay? The probability of getting a result as extreme as we got, assuming 63 is the center, assuming the null is true. That's what the p-value is based off of, is the normal curve where 63 is the center, or 63%. Finally, we write a conclusion for the fourth point, and the conclusion is going to have three big parts in it. It's going to have your p-value compared to your significance level, okay, which in this case, our p-value is about 0.147. Significance level typically is 0.05, and so we had a p-value, of course, greater than 0.05 here, so we'd fail to reject the null hypothesis. So that's the second big part, is decision. Again, if p is low, reject HO. So if p is less than, again, typically 0.05, we'd reject. If it's not, we'd fail to reject. Sometimes that 0.05 changes, but if p is low, reject HO. And then finally, you would say, so there is or so there is not evidence for HA, and you'd say that in context. Okay, so since we failed to reject here, we would say there is not significant evidence to support the alternative hypothesis that the percent of students who speed is something other than 63%. Again, when we go two-sided, it doesn't answer quite as much here for us, but we essentially didn't have enough evidence to disprove, or at least have evidence to show that it wasn't 63% based off of our sample. So make sure you include context here. And again, rejecting means there is evidence. Failing to reject means there is not evidence for the alternative hypothesis, which is what you always talk about there, because what always guides these questions is HA. We are trying to find evidence for HA, so our final statement will be about HA. All right, so that's the test side. We'll go much quicker through the rest of this. For an interval is typically a 3-point question. And this point here, this is typically not a point, but a parameter estimate is just kind of a thesis statement. So in this case, we'd be estimating the true proportion of students who's at Minnetonka High School, or student drivers at least at Minnetonka High School, who speed. And so we're just telling the reader what's to come here in this confidence interval. And again, the idea with a confidence interval, instead of actually testing a hypothesis, a confidence interval is like throwing a dart at a dartboard. We are just using our sample to try to state something about the greater population. Okay, so this would be used very commonly in terms of, you have a population that's really big, you don't have the time, money, energy to ask a question of, or to find something out about the entire population. So you pick a random subset, a random sample, and you use that sample then to make a generalized statement about the population that, again, is a match in terms of your sample came from that population. In other words, we can't use Minnetonka High School students to talk about other high schools. It would just be about Minnetonka. If we wanted to talk about other high schools, we'd have to expand our population for from whom we picked our sample to those high schools as well. So we might have 5 high schools, and we'd have a bucket of names from all 5 high schools, and we'd pick it out. And so that would have to be our sample. So here, we're just using Minnetonka High School students to estimate the population speeding percentage for Minnetonka High School students. To 1 proportion Z interval now. We use p hat now instead of p naught for that normality condition. Okay, the SRS stays the same. If we were to use the 10n is less than capital N, that would stay the same. But the normality condition changes because now we don't have a hypothesis. So our next best option is to use our sample p hat. So here we would have 100 times 0.7 and 100 times 0.3. So we'd have 70 speeders and 30 non-speeders in our sample, which of course both of those are greater than or equal to 10. So we could say it's fair to believe the sampling distribution would be normal. Again, this is successes and fails. So in this problem, successes represent speeders and fails represents those who don't speed. That would be a point right there to list the type and the conditions. Okay, then we get to the calculation, which would be the next point. Okay, so this is 1, this is the second point. The second point here, again, you're probably going to end up using your calculator. But if we wanted this to be a 95% confidence interval, then p hat would be our 0.7, n would still be 100, and z star would be 1.96, which we'd get from the chart. Again, if it's a 90% or 99% confidence interval, that z star value will change. But z star represents how many standard deviations either direction we are going to go for our confidence interval. Okay, so this collectively is the margin of error. Okay, that you would, just like you'd see on TV, margin of error. But here, in order to actually get this interval, what you're probably going to do is a stat test 1 proportion z interval, which is a little further down. Okay, and in the one proportion Z interval, you are now going to put in again X and N, which is 70 and 100. You'll put in your confidence level, and it will give you the interval. Okay, so the interval here ended up being about 0.6102 to 7898, which just means in this case that our margin of error was about 9% either way, as you can see, from 70% down to 61 and 70% up to 79. So our margin of error was about 9%. But in the end, based off of our sample, again, even though our population is 1,000 students plus, we can say we are 95% confident that our interval from 0.61 to 0.79 contains the true percent of Minnetonka student drivers who are speeding in the parking lot. Okay, so again, you have to give the context at the end here. You have to put the percent confidence, again, which is typically 95, in the interpretation, and you put those values, and again, those values represent the range of population proportions that we think it could be. Okay, we know this is just with 95% confidence, and so that just means in the long run, if we were to run 1,000 intervals, we would expect about 950 of them to contain the true mean. We know sometimes it's going to miss. We don't know when, but we just know the method we used in the long run, 95% of the time, it will contain the true proportion. All right. Two sample here. Now we just added another population. So this might be now Minnetonka males versus Minnetonka females. Okay. And we use the same context if we want to here. And so in this case, it's again speeding drivers. So what we would be looking at here is the proportion of males who speed in the parking lot equal to the proportion of females who speed in the parking lot? With the alternative in this case being, perhaps you might say, do males speed at a higher rate than females speed? Okay. And so we would be, again, basing this alternative off of the question. The question will ask what proportion, or the question may state, is there evidence that a greater proportion of Minnetonka driving males speed versus Minnetonka driving females? So now that we've established our hypotheses and what we're trying to find evidence for, again, that the higher percentage of male speed, we do have to explain what P sub M and P sub F stand for. And you can use whatever subscripts you want here. You could write out male and female total. You could use 1 and 2 if you want to, but again, you have to explain what each one stands for. So P sub M, of course, is the proportion of male drivers at Minnetonka High School who speed. P sub F would be the proportion of female drivers at Minnetonka High School who speed. That'd be 1 point. Second point would be typing conditions here, which is a 2 proportion Z test. The 2 SRSs, that could be one of 2 things. So first of all, it could be truly 2 SRSs, which it would be in this case. They'd have to say something like a random sample of 50 males and a random sample of 50 females, and we would again quote them. It could also be that it's an experiment. Okay, in this case it wasn't, but if it's an experiment, rather than a random sample, it might be that there were 100 volunteers and they were randomly assigned to 2 groups. And so you would just say there was random assignment of the subjects to the 2 groups. And so that's another option besides just a random sample or 2 random samples here. Normality condition. What you're going to see here is there is not one that's based off the hypotheses in this on the 2 sample. They're all based off the sample. And what you do is just go through each one and make sure there were at least 5 male speeders, at least 5 male non-speeders, at least 5 female speeders, and at least 5 non-speeders for females. And so if P hat sub M was 40 out of 50, and P hat sub F was 30 out of 50, what you'd find here is that we had 40 male speeders, which of course is 5 or more. We had 10 male non-speeders, which is 5 or more, and then 30 and 20 for the females. This would be sub F, sorry. And so you could do those calculations, or if they give you the fractions, you can just note each one of them based off the fractions. But again, it's essentially a numerator and then what's left. numerator, and then what's left for each group that you're testing to make sure is 5 or more there. If so, we can assume that it's an overall normal sampling distribution between the two populations. The third condition here is the idea that it is fair to believe that they're independent of each other. And that is just a statement. There's not going to be a lot in the question that will help with that. It might say that a random sample of 50 males and an independent random sample of 50 females was selected. So then you just note that it said an independent random sample. But otherwise, you could just say, make a statement, fair to believe that they're independent of each other. And you should make that statement just to say that essentially we aren't working with jaded data here where one group is influencing the other. Lastly, you could do a 10 times n sub male is less than capital N sub male, and 10 times n sub female is less than capital N sub female. Again, that's just the independence one within each group, that the males are independent of other males, that the females are independent of other females. But a lot of times that gets overlooked as long as the samples are random or there was random allocation in an experiment. In terms of the calculations, now the calculation here for the two proportion Z does include a pooled p hat in the denominator. P hat pooled in a problem like this is just the numerators added up over the denominators added up. So it's essentially like the weighted average of the two samples, which in this case is just the average of the two samples since they are both samples of size 50. So that's p hat pooled. You can actually get around even writing anything about that, because in this unit, in the inference units, if you use your calculator to complete the test, in this case you'd go stat. Actually, let's go blue here. You'd go stat test, and this is a two proportion Z test. Okay, and you'd put the values in, which in this case, because I listed males first, I'm going to put the males fraction in first, which is 40 over 50. Again, it's going to have x1, n1, x2, n2. Okay, and so that's the first one is the fraction for the males. The second one is the fraction for the females. My alternative is that it's greater than. And if you do this, then you do not have to write the formula. For either one or two proportion, you can do this, where you do not have to write the formula. You just have to write the Z, which in this case was about approximately 2.18, and the p-value, which in this case, actually I should probably write p-value just to not confuse with p here. P-value was 0.0145. Okay, so this is what you would write for that in order to get the points for number 3. And finally, you'd give the conclusion, which is based on our evidence. The 0.0145 is less than if we use 0.05. Obviously not less than 0.01 if we have to use that, but if it's less than 0.05, we'd reject and we'd say there is evidence that males speed at a higher rate than females, or that the percentage of male Minnetonka drivers whose speed is higher than the percentage of Minnetonka female drivers whose speed. So that's what we are finding in that problem. The final is the two proportion Z interval. And the two proportion Z interval, again, this kind of optional step is now we are trying to define or estimate the difference in percent of males versus female drivers who speed at Minnetonka High School. And the big thing is it's nice to be able to say which one minus which one. So I would say in this case, PM minus PF, just to denote for the reader that it's males minus females here. Okay, so now I have a definition of what I'm estimating, and now the big 3 points here. Okay, the type and conditions. This is a two proportion Z interval. Again, it's two random samples, and we'd quote the question, or if it's an experiment, we'd note that it's randomly assigned to two groups. It's the exact same normality condition this time. So you do not change it up like in the one proportion where it changes between interval and test. Okay, those are the same here. It's still independence between, and the whole 10n idea can still be in play if you want it to be. But otherwise, what you're going to see here is for all of these conditions are the same for a two proportion interval versus a test. Then the interval itself, again, p hat 1 I've described as being the males. So anywhere where I have p hat 1, I'd have the 0.8 or 40 out of 50. Anytime I have p hat 2 would be the females, which is 30 out of 50 or 0.6. And then the N1 would be the sample size for the males, which was 50. The N2 would be the sample size for the females, which is 50. But again, you can avoid writing this under two conditions. Did you identify already that it's a two proportion Z interval? And then as long as you write the actual interval, which you can get from your calculator, which would be stat test two proportion Z interval. Again, you do have to make sure to denote the type of procedure in order to be able to do this. Otherwise, we don't have the clarity of where your answers came from. So this would be a two proportion Z interval, which is a ways down on your calculator. And again, it's going to have xn, and that's just numerator, denominator. Again, make sure you put them in the same order as you defined already. So I had males minus females. So I'm going to put the male fraction in first, and then the female fraction in next. So it's 40, 50, 30, 50 in this case. I'm going to go with a 95% confidence interval, and that gives me the interval 0.0247 to 0.3753. Not real surprisingly here, 0 is not in our interval. That just shows that males do have a statistically higher percentage based on our interval. So we'd say we are 95% confident that our interval from 2.47% to 37.53%, kind of a wide range there, does contain the difference in proportion of males minus female speeders at Minnetonka High School. In other words, males are speeding at a higher rate, somewhere between 2.5% higher rate of speeding amongst males, all the way up to potentially about 37.5% higher rate of speeding amongst females. And that's with 95% confidence. Again, a big point of that is, at least based on our interval, we would have significant evidence that males are speeding at a higher rate. In order to use that to replace a test, that's one final point, that if an interval and a test match up properly, you can actually interchange them. By matching up properly, what that really means is two things, and I'll end with this here. In order to match up properly, the confidence level and the significance level should add up to 100%. So in other words, if I'm using a 5% significance level and a 95% confidence level, that means that's one threshold to use a test and an interval interchangeably. And what I mean by interchangeably is you'd get statistically the same result in terms of evidence for or not evidence for an alternative. The other thing is HA really needs to be not equal to. I won't get into specifics here, but if it's a one-sided alternative, since that's just really one side of the curve, whereas an interval slots dead center, so there's space on both sides of it, there's a mismatch there. So HA does need to be not equal to, which it's not on this slide, but it was on the previous, in order for an interval and a test to be truly interchangeable. So in this case, it didn't work out that way because our HA was greater than, but we did find in our interval, at least, that there was evidence that males sped at a higher rate. And we also found in our test when we rejected that males speed at a higher rate. So it did work out here, but you got to be careful using them interchangeably if we don't meet these two criteria. Then there could be little dead spots where the conclusion is different between the interval and the test. Thank you for listening. Sorry for the length and hope that helps. If you have questions, please ask.